When we look towards the center of our galaxy, we see something very strange. We see these stars moving around some points with very high velocities on very close orbits. It seems to suggest there is something there, something that we can't fully see when we point a telescope towards it. Of course, we now know what that thing is. It's a supermassive black hole called Sagittarius A star. And if we take lots of telescopes from all around the world and we point it at that spot in the sky, we can see this thing, this very mysterious object. Now, this black hole, it takes up a region in the sky that is equivalent to a tennis ball on the moon. So this is a tiny, tiny thing when we look at it all the way from Earth, but we're able to see it now. But I want to ask, what actually is a black hole? You might have come to another talk here previously on black holes, and you might have heard something amazing about what they do in our galaxy and the universe. But there's always more questions, there's always more things left to answer about these mysterious objects. So what I want to do today is to try and give an FAQ, frequently asked questions about black holes, and try and answer some of those burning questions you might have. So I've done a bit of research and I've thought about some of the questions that you might reasonably want to know about, and I'll just list them here so we have a bit of an idea about what we're going to talk about. So what is a black hole? That's a good starting point. What is a black hole? We're going to talk about that. What are they made of? What actually is a black hole made of? What's inside a black hole? And is it a four-dimensional bookshelf? Because if it is, I've got a great idea for a film. What's on the other side? Is it a parallel universe? That's me being a bit sensationalist. As a respectable astrophysicist, I should add almost certainly not a parallel universe. But I'll explain why that's a possibility, or at least why people might think that. Never mind a black hole, what's a white hole? I get this question, what's a white hole? I'm bored of black holes, I want to know what a white hole is, so we'll talk about that as well. And finally, should I be worried? I suppose we can disaggregate that a little bit into should I be worried, generally speaking. I'm not really qualified to answer that question, but specifically regarding black holes, that is something I can do. So we can come to that at the end. And just to show that I've really been putting the work in and I've been doing my research, I went on the internet and I typed in, what does a black hole? And I let Google autofill for me. This is the best way to figure out what people on the internet are asking. I should preface this by saying there are no stupid questions in astronomy. No stupid questions. Every question is a good question. But people on the internet want to know, what does a black hole taste like? I'm going to put my hands up and say, I have no idea. Maybe spaghetti. I don't know. So, like any good story, this one starts with Albert Einstein. About 100 years ago, he came up with a theory of gravity that superseded Newton's theory. He said that the universe is made up of a combination of space and time called space-time. And what happens is space-time is curved and warped by the presence of matter. And in turn, the bending and warping of space-time tells matter how to move. Now, it's quite nicely summarized, I think, in this article here. So, space of 4 dimensions, not exactly its space of 3 dimensions and 1 of time, but that's the kind of idea. We live in this 4-dimensional space-time. Gravity ceases to become a force. Okay, that's not exactly true. I would still call gravity a force, but it's certainly true that it behaves very differently from the other 3 forces of nature. So this is very interesting. Gravity behaves very weirdly. It's very unusual. Attempt to measure it. The thing is, every test of gravity that we've done, every test of general relativity, has agreed with Einstein's theory. Every observation that we've made has perfectly agreed with Einstein's theory. It's one of the best theories of nature that we have. And yet we know that it must be wrong. Not entirely, but it is at least incomplete. There are certain features that we can't explain everything with the theory. And we'll come back to that in a second. But this is my favorite bit of the article at the top over here. So Einstein's general relativity is a series of 10 coupled differential equations. It's very difficult to manage. It's quite hard to work with. It's not as simple as it first appears. So in this article, they say, Sir Oliver Lodge, who was a physicist at the time, says it will prevail. And mathematicians will have a terrible time. I don't know why he said that. There's probably lots of other ways you could word that. Mathematicians were just having too much fun in the 1800s. Needs to be brought back down to earth, if you'll pardon the pun. So moving swiftly on, despite the fact that general relativity is so difficult to manage, it only took, or to work with, or to do the calculations on, in only a month after Einstein published his theory, on the front lines of the First World War in Russia, a man called Schwarzschild found the first solution. And this was the simplest possible solution you can imagine. It was take a flat plane of space-time and place a mass at the center. We'll add some coordinates in. We'll say that there's a radial coordinate here. We'll set the mass to be equal to 0. And then as you move further away from the mass, R increases. We get further away. It's as simple as that. And we'll have a time coordinate as well that measures the clock ticking. Now, the interesting thing about Schwarzschild's metric, the solution to one of the solutions to Einstein's equations, is that there's a problem at this point, at r equals 0. Something explodes. And it's because you have to divide by 0. Dividing by 0 is a problem because it's undefined. Stuff gets very big very quickly and in a way that's totally unphysical. What's also interesting about Schwarzschild's metric, or his equation, is that there's another place where things go wrong, further out, at the Schwarzschild radius, Rs. This is another place where the equation explodes. It's another place where you divide by 0. So what that's kind of telling us is something very strange is happening at these two places. And Schwarzschild's equation is not sufficient on its own to tell us what's going on. So if you're a mathematician in the room, you're probably thinking, how do we avoid dividing by 0? That's undefined. We can't do that. It's not allowed. If you're an astrophysicist, you're probably thinking, how do we translate this thing here, which will eventually become a black hole, into something we can go and observe? And if you're in neither of those two categories, you're probably thinking, am I going to include more explosions in my PowerPoint? So that I say, what do you take me for? Okay, there's one more explosion, one more, but we're moving on. Okay, let's investigate the Schwarzschild radius a bit more closely. We'll start with the second of those two places where the equation explodes. And we'll imagine moving a clock, throwing a clock into the black hole. And this is what we see. As the clock approaches this point, the Schwarzschild radius, it slows down. The ticking slows down. It's as though time is slowing down for that object. When it hits the Schwarzschild radius, it freezes entirely. It completely stops. That means everything that falls into a black hole freezes at this point. Every single thing. What also happens is these objects get redshifted. Any light they're emitting gets stretched by the pull of gravity and gets redder and redder until eventually it becomes invisible. So if you were looking a very long way away at this object, you would see things become redder and redder. They would freeze on this surface, and then they would disappear. But if you had a very sensitive camera, you might detect individual photons coming off these objects. So it's almost as though nothing can fall in. Nothing can get further than this point, which is very weird. I should also add here, don't try this at home. I don't know if that was obvious or not. Animal cruelty. And also Schrodinger's cat, like he already did that, putting a cat in a confined space, and it just led to convoluted thought experiments that we don't need. So now we can do something very interesting, which is take Schwarzschild's equation and rethink the coordinates. He chose perfectly reasonable coordinates that got us so far, but they didn't seem to describe the full picture because there are still these problems that remain. Stuff freezing on the Schwarzschild radius, and obviously the second point at the center. So two people called Eddington and Finkelstein had this idea to change the coordinates that we use in the Schwarzschild equation. And they adapted the coordinates to be suited to light falling into the black hole. When we do that, we find something very strange. Well, we can use this diagram. So we've got the same radial coordinate moving along the bottom, and we have a time coordinate moving on the top axis, on the vertical axis. So this is a kind of space-time diagram. And so you might want to think about this for a second, but you can imagine that if you want to send something into this object, it will move along the horizontal axis, but then time ticks forward. So it's also moving upwards at the same time. So generally speaking, we would expect these diagonal lines across the diagram. And for light, which is the fastest thing there is, these diagonal lines will just move straight across. And what we find when we use these new coordinates is they don't stop at the Schwarzschild radius, but the light is able to pass straight through into this inner region. So in these adapted coordinates, we don't need to worry about things freezing anymore. If you're falling into the object, you will pass straight through. So this was light that's moving into the black hole. They also said, what about stuff moving out of the black hole? So if you're one side of the Schwarzschild radius, you just exit, you go back into the universe, and everything's fine. If you have outgoing light that's on the other side, on the inside of the Schwarzschild radius, oh, seems to head in again. So even though we want it to be heading out, it seems to be falling in. Now what we can do is we can create these regions on our diagram called light cones. Light is the fastest thing there is. Everything in the universe that has mass, so us, rockets, whatever it might be, must inevitably travel slower than light. And so on these diagrams, these kind of green regions, these cones, these triangles, represent regions in which things like us, people and objects with mass, are allowed to move. So we can only move within this green region here that kind of extends outwards, with light representing the limits of where we're allowed to go. So what this diagram is telling us is that not only does light never leave this point, but we wouldn't be able to either. So you can see the green triangle over here on the right-hand side of the diagram. That allows you to kind of traverse the rest of the universe with little trouble. But if you're on the left-hand side, you can see that the cone lines up with the Schwarzschild radius and then moves inwards like this, towards r equals 0. So the only trajectories that are allowed take you further into the black hole. What we're saying is that this line represents a point of no return. Things traveling past this point must inevitably stay inside this region. So we call it the event horizon. It's the point of no return. So this is what the second explosion, the second divide by zero in Schwarzschild's equation was telling us. It was telling us that there's this very strange point where from afar, it looks like things freeze on this surface. But if you're the one traveling in, you're able to travel straight through. But once you're there, you can never get out again. Nothing can escape this region. So this is how we define a black hole. So you can forget about the definition relating to stars collapsing or anything like that. The formal definition of a black hole is the region of space-time from which you can't send a signal out to the rest of the universe. It's the region where things have to be trapped forever. So that answers the first question. It also answers the second question, which is what is a black hole made of? It's made of space-time. That's all it is, the same stuff that the rest of the universe is made from. It's just a particular configuration where the flow of space-time inwards is so great that nothing can escape, not even light. So the next question you might be thinking is, can we do this same trick of shining light through the event horizon? Can we do that with the point in the middle, which we call a singularity? Well, the answer is no, we can't. These coordinate tricks don't work at this point. Something even stranger is going on here. In fact, if we compute the curvature of spacetime at this point, we find that it blows up as well. This represents a physical singularity. Well, we call it a physical singularity, but in reality, it's not actually physical. And this is where Einstein's equations break down. This is a point that we can't fully explain. This point right at the center of the black hole. It's incredibly small and very heavy. And it suggests to us that maybe we need a new theory. We either need an extension of Einstein's general relativity or a totally new theory, something that combines general relativity and quantum mechanics, things that are very small, into one unified theory. The answer is this thing in the center. But the trick that the universe plays is it always hides it behind an event horizon. So astronomers can't see it. So it's as though the universe is kind of hiding these paradoxes from us. What it's saying is that we need to think harder. We can't fully explain this object, but we can still work with it for now. What I wanted to do is take this a bit further. We can't do the same coordinate trick at the singularity, but there are other ways that we can manipulate the Schwarzschild equation and turn it into something even more. So there's a thing called a Penrose diagram, which looks a bit like this. It looks a bit imposing at first, but I'm going to try and explain it to you now. I'll tell you the important features that will help you to understand it. So you can kind of think of space as moving along the horizontal axis and time as moving along the vertical axis into the future. So these edges over here represent spatial infinity. So this infinite universe is being compressed to a finite area. This line here is the event horizon. This region 2 here is the black hole. This zigzag line up here is the singularity. And this region here, region 1, is our universe. So what we're doing is we're kind of shifting the way that we view the map of our universe and the black hole. That makes it more tractable. It allows us to kind of think about it in a slightly different way. The most important thing about this diagram for now is the fact that light moves on these 45-degree paths, either that way or that way. And so thinking back to earlier when we were talking about these light cones, this fastest possible speed that we can travel, this region inside the light cone represents where we can travel with mass. So you can imagine whilst we're in the universe, we might enter the past light cone here, and this is us at the present moment, and then we're allowed to travel in this region here, but we can't travel over here or over here, because that would be outside the light cone. So now if we move the light cone to the event horizon, you can see that one of the boundaries sits on the event horizon, and the other one travels into the black hole. So this is another way to think about the inescapability of a black hole. Once we're at this point, we have to travel towards the singularity. And this is why you can never leave a black hole. Another way, a cool way to view this that I quite like is you can think about never leaving a black hole as the fact that we can't travel faster than the speed of light. But remember that I said that time moves along the vertical axis, and this is the future going up. You can see that when you're in the universe, you travel up into the infinite future, which is this point up here. When you're inside the black hole, the future is the singularity. So now when you're inside the black hole, the singularity is no longer just a place in space. It's a moment in time, and it's a moment that inevitably lives in your future. The reason you can't escape the singularity inside a black hole is the same reason we can't escape the future. Because you have to inevitably move towards that line. So here's an example of a possible path that we might take into the black hole. Through the light cone, across the event horizon, and into the singularity. Now, when you're looking at this diagram, if you imagine placing this light cone at this point here, this projects forwards and gives us the black hole. But there's also the past part of the light cone here, which represents where we could have come from to arrive at that point there. It looks like there could be something in the past of this black hole. And there is. It's something that looks a lot like a black hole, but reversed. Now, there's a few interesting things about this object. You can see that from our universe, there is no way to enter this thing. There is no path that we can take that allows us to get into it. But when we're inside, we inevitably must leave this object. So nothing can get in, but it pushes everything out. This is a white hole, a time-reversed black hole. Now, you can see that there's a region missing over here. So we'll fill that one in as well. This is the fully extended coordinates of the Schwarzschild equation. This region, number 3, looks a bit like our universe and kind of sits alongside it. You can think of this kind of like a parallel universe, and it just falls out of the maths. Again, you can see that from our universe, there is no way to get to this parallel universe. It's impossible. But let's say you had someone in here and someone in here. You could both go into the black hole. You share the same black hole. You could say hello to this person from a parallel universe and then both get inevitably crushed by the singularity. So it's kind of up to you, really. But this is very interesting. So now you can see where this idea of a white hole comes from and this idea of a parallel universe. It's very cool. Now we have the idea of a black hole. Up until this point, everything I've said has just fallen out of Einstein's equations. We've not made any reference to stars or the universe or anything. This is simply mathematical. What's remarkable is the possibility that this thing could exist at all. And it takes one person who you'll all be very, very familiar with to fill in the next piece of the puzzle. This person here. Sorry, no, this person here, Oppenheimer. Sorry, 2023 really messed with my brain. This guy. So Oppenheimer, with a few colleagues, Volkov and Tolman, and also one of his students, Hartland Snyder, were thinking about the collapse of stars. Now, up until that point, people were aware that when a star collapsed, it would freeze at some point because of pressure pushing it outwards again. So once the pressure due to fusion had ended, it would start to collapse inwards, but other quantum sources of pressure would push it out and keep it stable. What they found, though, is that if the star is big enough, it will just keep collapsing. It will collapse down and down and down, and it will cross its own event horizon. And we know that once it's crossed the event horizon, it makes a black hole. It's as simple as that. What they showed in this paper on continued gravitational contraction is that black holes can form in the universe. Black holes can form from dying stars. And then, 25 years later, we saw X-rays from the constellation of Cygnus, coming from a binary system of a star and another compact object. And there was this paper published on it. And in the paper, they say, we should also speculate that it might be a black hole. It was a black hole. Since then, we found many more black holes. These are real-life things that actually exist in the universe. Pretty amazing. It does mean, though, that we need to go back to our Penrose diagram. Because I know what you're thinking, really, is where are all the white holes and where are the parallel universes? The problem is, this is for an idealized black hole. This is for a scenario where the black hole has been around for eternity. It's time symmetric. Everything in the scenario is very symmetrical. But the formation of a black hole is an inherently time asymmetric process. It forms from gravitational collapse. And so what we're forced to do is slice off parts of the Penrose diagram. And we're left with this. So we have our universe here, and we still have the black hole, but unfortunately we lose the parallel universe and the white hole. I know, very sad. There is no known physical mechanism for the production of white holes. And we have lots of reasons to think that they almost certainly don't exist in the universe. But that's fine, because we still have black holes, and black holes are pretty cool. But it does raise a more important question, which is, how does theory relate to observation? Because all these equations, all the maths that we can do, tell us about what's potentially viable in the universe, but we then need to go out and actually test it. And this is an astrophysics talk, so we're interested in what we can see, what we can observe. So how do you test whether this thing, in theory, is the same as the things that we see when we look out into the sky? Well, one of the best ways to do it is with gravitational waves. Gravitational waves form when black holes merge together and send ripples through space-time all the way to Earth, where we can detect them using pieces of equipment like this, detectors like this one. This is remarkable. We've only been able to do it for about 10 years. We've only been able to hear these for about 10 years. And in that time, we've detected about 100 of these events. I should add that these are some of the most powerful events in the universe. The first gravitational wave event that we detected was so powerful, it released more power than all the stars in the known universe combined. So these are monstrous. These are extremely loud, energetic events. And we can convert the gravitational waves we detect into sound, and we can hear them. So prepare to hear one of the most catastrophic events in the entire universe. Okay, moving on. We can also simulate black holes. And this makes mathematicians have less of a terrible time. We can take the equations and we can put them on a computer, and we can see what happens. So this is a simulation from a collaboration that I use. I use these kind of simulations. And you can see the black holes merge together. They reach this point where they merge, and then we're left with a single black hole. And the gravitational waves propagate out into the rest of the universe. And so now we have a theoretical prediction using numerical relativity simulations, and we also have real-life data. And so this gives us the opportunity to compare what Einstein said and what we can see. And hopefully somewhere along the way we'll learn something new and maybe even build on Einstein's theory or change it entirely. So I think that leaves us answering most of the questions, except for maybe, should I be worried? I mean, obviously we shouldn't be worried. Obviously not. None of you were anyway. But I think this is pretty remarkable. And a point that I didn't mention is that Oppenheimer published that paper on gravitational contraction on the day that the Second World War broke out. So in both Schwarzschild and Oppenheimer's case, these discoveries came under the shadow of world wars where humans were kind of bent on destroying themselves. But we're also capable of doing so much more. And you can see that here. We're able to predict something from equations, go out and observe it, hear gravitational waves from these distant black holes billions of light years away, and see these things within our own galaxy and study them, which is pretty remarkable. So of course we shouldn't be worried, we should be excited, because this is amazing. It shows that what we're capable of doing, and it shows what's out there as well. And hopefully you see that as well. That's everything. Thanks.